the initial call. Okay. Switching from baseball to probability, although we will get back to baseball later this semester. So what we're doing is we're continuing to go through stuff up through, I think, chapter 16. So you should have read all the material by now, and what I want to do is I want to start showing how everything pieces together. This is the chance to show off your integration skills, okay? As well as to see ways to avoid having to show off your integration skills. We will really see that when we get to the chi-squared distribution. The chi-squared distribution is going to involve, in general, having to integrate over the n-dimensional sphere. How many of you remember your spherical change of variables coordinates? Okay.
There's P, theta.
First of all, it's not P. That's unacceptable. You have to use rho or R. You can't use P. Especially in a probability class.
Okay. There's R.
Okay.
But it's R in like 3 dimensionals, so it's not like
Right.
just a 2-dimensional R.
But what's the change of variable formula? What does the volume element go to?
Square root of.
So who knows what the volume element is? And so
Rho squared
dx,
sine
dy, dz goes to
rho squared sine phi d rho d phi d theta.
Okay. You are correct if you can correctly tell me which angle is phi.
The altitude across the z-axis.
I'm sorry?
The angle from the
I believe
z-axis.
so. So there's
multiple conventions.
There's multiple conventions. I was trained by the physicists, unfortunately, so I often have trouble in math classes. The physicists and the mathematicians interchange the role of phi and theta. When you get to the 4-dimensional sphere, it's no longer a problem because they just use theta for everything. Okay? So you have a formula like this. You have x then becomes, okay, so this is rho, this is rho cosine phi. So I think it's x is, I think, rho cosine theta, cosine phi, or maybe sine. You got to play all the games to see how things go. The point I want you to see right now is you don't want to do this. Okay? You want to find ways to do integration without explicitly writing everything down. Which is interesting because I then, in the spring we'll be teaching Math150 where we'll be doing nothing but writing all this stuff down. But you've paid the price. So what we're going to do today is we're going to learn how to avoid doing a lot of that. So what I want to start off with is Gaussian mean variables. And so you often call them the bell curve as well, or the normal distribution. As a rule of thumb, the more names something has, the more important it is. There's at least 3 different names for this distribution. All right? So we say x is n mu sigma squared if its density function is 1 over the square root of 2 pi sigma squared e to the negative x minus mu squared over sigma squared. Okay? So when you look at this, what should you be thinking about mu? What should you be thinking about sigma? Yes?
Sigma shouldn't be 0.
Sigma shouldn't be 0. And what quantity, what does sigma represent, or sigma squared represent?
Variance.
So sigma squared should be the variance. And what about mu? Mean. So if I'm going to use this as my notation, if I want to be consistent with everything else we've been doing in the class, what we should do is this distribution should have mean mu and should have variance sigma squared. If not, this is horrible notation. Oh, it is over 2 sigma, thank you. Yes. Okay. What is the best choice of sigma to take? 1. And if you take 1, when people are writing it, are they writing the parameter as sigma squared or sigma when they're defining the normal random variable? If it's 1, it doesn't really matter. Okay? So you have to be careful. Most people will do n mu sigma squared where they're putting in the variance. Okay? Other than the who gives a damn question, what is the first question you should be asking when you see this? I'm sorry? Does it integrate to 1? And I guess looking at this one, it's very clear that this is going to be non-negative. So we're just down to, does it integrate to 1? That's going to be the difficulty. How many of you have seen the calculation that this integrates to 1? Have you seen the polar trick?
Possibly.
Okay, so we're going to prove that this integrates by 1 by doing a very strange trick. It's one of my favorite tricks in mathematics. Later, probably on Monday, we'll get to the gamma distribution, and we'll see a way to interpret this and all of its moments in terms of the gamma function. And so the more you know about the gamma function, the more you can actually calculate here. All right, so the first thing is, let's show that it integrates to 1. So we want to integrate from minus infinity to infinity 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx. The first thing to note is that we can do some change of variables, and it's enough to consider a special case. What special case would you like to consider? So we've got two parameters, mu and sigma. If you could choose.
Mu equals 0 and sigma equals 1.
Yeah, we want to basically say if we can do the calculation for mu equals 0, sigma equals 1, we can change variables and get any other case. So one good change of variables is let's let u equal x minus mu over sigma. And then du would be dx over sigma, or I can write it as dx over the square root of sigma squared. And I'm writing it like this to just make it really clear with what I have here. So as x goes from minus infinity to infinity, u is going to go from minus infinity to infinity. This is the same as integrating from minus infinity to infinity. I lose the sigma squared when I change the dx, so I get 1 over square root of 2 pi e to the minus u squared over 2 du. There is something else I could have done. Instead of changing variables with x minus mu over sigma, what else could I have changed to? And this goes back to something Lily was calling me out on a moment ago. I think we had a class agreement that we don't like fractions last time. Right? When I'm changing variables, I'm keeping the 2 over here. Do we want to keep the 2 there, or do we want to get rid of the 2? Let's get rid of the 2. All right, so if we want to get rid of the 2, all I have to do is replace these with what? Square root of 2. And so now I'll have square root of 2 sigma. I lose the 2 over here, and now I lose the 2 over here. Is that a good trade to do? Yeah. Yeah, it makes the algebra a little bit cleaner. So it's enough to study this one. So notice what in the end we study is not mean 0 variance 1, but mean 0 variance 1/2. And there are long discussions we can have as to why we want to normalize it with the 2 down there, and I promise you we will have those at some point. Alright, so now we want to evaluate this integral.
Wait, so how did you just slash those two?
Well, I just did a different change of variable. I let you have now a square root of 2
Okay.
down below.
Okay.
And so when I square that, I'm going to get an extra factor of 2. So the first question, of course, is whether or not this integral converges. So does this integral converge? So one question is, what kind of decay do we have? Well, if u is very large, e to the minus u squared is decaying very rapidly. Unfortunately, the big lie of Calc 2 is that you can do integration. We don't know a nice function whose derivative is e to the minus u squared. Can you give me a function that's larger than e to the minus u squared that you can integrate?
E to the minus u.
Excellent. So if the absolute value of u is greater than or equal to 1, e to the minus u squared is less than or equal to e to the minus u. And that we can integrate. Or maybe I should be a little bit careful. I'll put absolute value of u over there. Does that relationship hold if the absolute value of u is less than 1? Is e to the minus u squared still less than or equal to e to the minus u? No, put in u equals 1/2. E to the minus 1/4 is larger than e to the minus 1/2. But that's okay. The interval from minus 1 to 1 is going to give a finite contribution. So we can use this over there. If the absolute value of u is less than or equal to 1, it's a finite contribution. So again, whenever you're doing calculations, it's nice to see, does the calculation make sense? Is this an integral we expect to exist? There is enough decay, so this is possible. All right. I'm now going to show you the strangest way to evaluate this. What kind of integral is this? What class would this be encountered in? Would you see an integral like this in Calc 3?
Rectangular or
No. Why wouldn't you see? What does Calc 3 study? What kind of integrals? Multivariable integrals. This is a one-dimensional integral. Let's give it a name. Let's call it I. I'm going to calculate I squared. Alright? I'm going to write I squared as the integral from minus infinity to infinity, 1 over square root of pi, e to the minus u squared du, integral minus infinity to infinity, 1 over square root of pi, e to the minus v squared dv. Remember, u and v are dummy variables. I could use the same letter u again, because I've completed the integration, It's much better to use two different variables. If you use the same name, you might mistakenly think it's just one integral. It's two integrals. Could I use a smiley face, I've said this before, as my variable? I'm sorry? Does he actually use smiley faces?
Yes, a lot.
Okay, a lot. If my daughter was here, she'd probably have me use a butterfly. Okay, my son would have me use a train. It doesn't matter what I use for the name of the variable. The point now is I can write this as the integral, let's pull out the square roots of pi. So I have a 1 over pi, because I have two of them. Integral from minus infinity to infinity, integral from minus infinity to infinity, e to the minus u squared times e to the minus v squared is e to the minus u squared plus v squared du dv. So the way I'm going to try to evaluate the single integral is I'm going to bump it up to a double integral and take the square root. So if you haven't seen this before, you've got an e to the minus u squared plus v squared. You should be thinking of something. What are you thinking of? Circles. So we don't have that many techniques in multivariable calculus, which is nice. We have switching the order of integration, but that's not going to really help you if you have rectangular for the most part. And we have change of variables. So here we want to do change of variables. So we want to use polar. So let's let u equal r cosine theta, v equals r sine theta, 0 less than equal to theta less than equal to 2 pi, 0 less than equal to r less than infinity. And we learned that du dv transforms to r dr d theta. While we always write r dr d theta, I don't think that's a good way to think of r dr d theta. Does anybody know how you should view r dr d theta? I claim you want to change the order of the multiplication of these three quantities. I like to view it as dr r d theta. Think of giving u and v units of meters. So when I'm integrating here, I have my surface area is meters squared. Angles are unitless. And so if I want to have a length, I have to multiply the angle by a length. And so if you take a circle, if I give you a circle of radius r and angle theta, the length of this arc over here is just r times theta. And so if I write it as r d theta, that's kind of reminding me that this is how I get my second length. My first length is my dr, my second length is r d theta. Alright, now that we have this, we can calculate I squared. So I squared either is or am, 1 over pi, integral r goes from 0 to infinity, integral theta goes from 0 to 2 pi. Now we have e to the minus r squared r dr d theta. Okay. And so, if I'm writing it in this order, I really should put the d theta first. And I actually want to put the d theta first, because the theta integration is the easier one. What's the integral of this for this? Ah, thank you. What's the integral of this with respect to theta? Is that an easy integral or a hard integral?
Easy.
Easy. There's no theta dependence, right? I'm just going to get 2 pi from the theta integration. It's going to cancel the pi down here. and you get 2. The integral r goes from 0 to infinity of e to the minus r squared r dr d theta. And actually, I'm going to put the 2 over here. Why do I want to put the 2 down there? Yes?
It suggests a u substitution.
Yeah, it suggests a u substitution. I have e to the minus r squared. The derivative of minus r squared is minus 2r dr. And so what I get is I get minus e to the minus r squared at 0 and infinity. Well, the minus sign means I flip the order of integration. And so I'll get e to the negative 0 minus e to the negative infinity. And that is equal to 1.
Yes.
And of course it has to be equal to 1 because we're doing a probability distribution. So, of course, when you initially start doing this, you don't initially know to put in a square root of 2 pi down here. That comes much later. This is why the normalization factor is the square root of 2 pi. Okay, so this is a nice integral to do. It's a really strange technique to evaluate a one-dimensional integral by converting it to a two-dimensional integral and actually making progress. There's another point that's worth emphasizing here. We want to calculate probabilities. We want to find areas under curves. Unfortunately, we can only integrate the normal in closed form from minus infinity to infinity. There's one other type of integral of the normal we can do in closed form from start to end.
0 to infinity.
0 to infinity. And of course, you could also then do minus infinity to 0. Those are essentially the only times we can easily write down the integration of the normal. In general, it is very hard to find a closed form solution for integration. And so, a lot of times you think you know integrals when you really don't. So what's the integral of cosine? The integral of cosine? Sine, right? What's sine? How do you calculate the sine of a number? Do you take a piece of paper, draw, take a really accurate ruler? How do you calculate the sine of a number?
The opposite.
I'm sorry?
The opposite side of the triangle with that angle.
So let's say I give you the sine of square root of 5 over 1701e. How does the calculator calculate?
Taylor series.
Taylor series. Sine is really an abbreviation for an infinite series. But because you've heard it so often, you feel comfortable with sine, and you feel confident, and you feel like, oh, I can integrate, I just get sine. You've just given it a name. Okay? The same thing is true here. When we try to integrate the Gaussian in general, we have this infinite series expansion, and it's a bit of a trick to get an infinite series expansion that converges well, and we give it a name. Except I think we give it a more honest name. We call it the error function. And there's some strange normalizations as to how you want to define things as to where do you put your 2's, which is quite annoying. The error function, I believe, is different from the standard definition in terms of where it puts the 2, which causes so much fun. Okay. We now have normal distributions. I'm not going to try to motivate why normal distributions are useful. You're in an upper level math class, so grades are not distributed normally anymore. But for the lower level classes, that is definitely one of the more interesting, important applications. If you have a normal random variable and you have another normal random variable, what's the natural thing to do? I'm sorry? Add them. So the question is, what can you say about the sum of two normal random variables? So let's let xi be normal with mean ui and variance sigma I squared. And we want to figure out what's the sum of two normal random variables. Or more generally, what might you want to consider? So we could sum two normal
random variables.
I'm sorry?
And
N random variables. So I claim that if you can figure out the sum of two normals, you can prove the sum. You can figure out the sum of n normals without any more integration. Okay. So let's just get a sense of how bad life is going to be. Okay. How do you calculate the sum of two random variables? How do you get its density? What do you use?
Convolutions.
You use the convolutions. right? That name should be a little bit scary as to how convoluted the argument is going to be, right? F of x1 plus x2 of x is the integral from minus infinity to infinity f x1 of x1, f of x2, well, let's use the letter t, x minus t dt. So in full glory, minus infinity to infinity, 1 over square root of 2 pi sigma 1 squared e to the negative t minus mu 1 squared over 2 sigma 1 squared e to the minus x minus t minus mu 2 squared over 2 sigma 2 squared dt. I'm sorry that you chose this class to walk in on. Okay. So who is really excited about evaluating this integral? Okay. Excellent. So now, what would happen if we had the convolution of even more things? We need more integrals. Or did I drop something? Oh, probably dropped
normalization.
another. Yes, I dropped another normalization. So what I will do is I'll pull both of them outside the integral. And we'll get 1 over 2 pi sigma 1 sigma 2. Because the square root, yes?
Why are we differentiating between the u's and the sigmas? Or
What?
x1 and x2?
Oh, I'm not assuming they're drawn from the same normal distribution. Maybe x has mean 5 and variance 3, and maybe x2 has mean 12 and variance 8.
Okay.
So I'm not assuming. So this is a really good question. If you had to choose values of mu1 and mu2 and sigma 1 and sigma 2 to do this integration, what would you choose initially?
Just like that.
Same values,
And mean 0.
mean 0,
Variance 1.
variance 1. So what you want is you want to do a change of variable that in some sense will allow you to pass to that case. But the important thing is we actually need the result in general. So what I want to do is I want to conjecture what the result should be. What can you tell me about the mean of x1 plus x2? It's mu1 plus mu2. We have linearity of expectation.
Over 2?
No, not over 2.
Oh, not over 2.
Right. If on average you get $5 from the first process and on average you get $8 from the second, if you now have both processes coming in at the same time, you get $13. What about the variance of x1 plus x2? And I'll assume that these are independent. If they're not independent, of course, we're up the creek. But let's assume they're independent. What should be the variance of this? So I want the variance of a sum.
The sum of the squares of variances.
So the sum of the variances.
Yeah.
Right? So the variance of a sum is the sum of the variances if they're independent. So this should just be sigma 1 squared plus sigma 2 squared. So if you think back to maybe the products, imagine you have processes that have mean 0 and variance 1. If you keep adding a bunch of them together, the variance wouldn't be growing if all the variances were 1. If the variances were 1/2, if you had a product, then the variance would actually be getting smaller the more things you add. And you shouldn't be getting more and more certainty as you're doing. So you want to try to think, can you look at some special cases? So we know the variance of a sum is the sum of the variances if they're independent. We know the expected value of a sum is the sum of the expected values, irregardless of whether or not they're independent. So we have some information about this distribution. Can anybody give me a conjecture for what x1 plus x2 should be? So it's got to satisfy these two constraints. What would be the nicest thing you could conjecture?
If it were a normal distribution with those.
Wouldn't that be really nice if the sum of normals is normal? So theorem. Normal mu1 sigma 1 squared plus normal mu2 sigma 2 squared is normal mu1 plus mu2 sigma 1 squared plus sigma 2 squared. If you think back to what we did earlier with rolling die, we saw if we rolled a die, the digits 1 through 6 are equally likely to happen. And if we roll 2 die, we don't have a uniform distribution again. We have a triangle function from 2 to 12. It starts off at 136 at 1, peaks at 736, and comes back down to 136. When you take two discrete uniforms and add them, you don't get a discrete uniform back. Here, we're taking two normals and adding them. And from that, we are then getting another normal back. What do you think happens if we have three normals?
We can group and
We can group. So all we have to do is, if we can prove this one theorem, we actually have the sum of n independent normals is exactly what you would expect. And the reason is as follows. I'll just do 3. So let's say we have these 3. I can add these two together. And that's going to be a new normal variable. And then when I add this, I'll have a normal variable as well. If you want to write in more normal notation, mu1 sigma 1 squared plus normal mu2 sigma 2 squared plus normal mu3 sigma 3 squared. So I first group these two together, and now I have normal mu1 plus mu2 sigma 1 squared plus sigma 2 squared plus normal mu3 sigma 3 squared. So this is again proof by grouping. This is one of my favorite techniques. If you can just do the n equals 2 case, you frequently get all the other cases for free. Well, now we're back to just using the n equals 2 case. And so this will then just be normal mu1 plus mu2 plus mu3 sigma 1 squared plus sigma 2 squared plus sigma 3 squared. Alright, so if we can just figure out that one special case in the beginning, we're done. Okay? Alright. So unfortunately, this is where it would be nice to have a classroom that had significant blackboard space. I want to keep the definition of the convolution on the board. So what I'll do is I'll just erase the very stuff at the bottom over here, and that'll give you a moment to just quickly make sure you've copied all this, and then we'll have to eat up that blackboard space as well. Alright, so we want to do the calculation for this integral. So the first thing we want to look at is possible changes of variables. Are there change of variables we can do that will make things nice? So what do you think? Can I get rid of both mu1 and mu2? Yes.
This may be completely off, but with differentiating by identities potentially, would there be a way of
Well, I do know that this, if I then integrate this over x, I would get 1. So I could try integrating this over x and then try to pull things over. But I want to know what's going on for specific x. X is fixed. I'm trying to find the probability density for a fixed x. Okay. So before I had this change of variables, I let u equal x minus mu over square root of 2 sigma. Can I do something like that over here? Can I fix both of these terms and get rid of both mu1 and mu2? So what's the only variable I have to control? T. So if I change t, if I replace t with t plus mu1, I can clean up this, but at a cost over here. Right? But what will I get? If I let t go to t plus mu1, I'll get a minus mu1 minus mu2. Hey, that's minus mu1 plus mu2. That's minus the expected mean. So that seems like that could be worth doing. So let's let u equal t plus mu1.
T plus or T minus?
I think I want t plus. Oh, I'm sorry. I've got t and u on the wrong side. I want t equals u plus mu1. And so when I plug that in here, I'll get a minus u squared over 2 sigma 1. And so now I'll get 1 over 2 pi sigma 1 sigma 2 integral minus infinity to infinity e to the minus t squared over 2 sigma 1 squared e to the minus x minus, oh, I'm sorry, I'm now using the letter u, x minus u minus mu squared over 2 sigma 2 squared du. And I'm letting mu be mu1 plus mu2. Okay. So I'm going to leave the statement of the theorem. If you have an idea of what you're trying to prove, this can help you find the right path through the algebra. What are we trying to prove? What's our goal?
That this integrates to 1.
Not that it integrates to 1. We know it integrates to 1 because it's a convolution of probability densities. So convolutions of probability densities integrate to 1. What are we trying to prove?
That it's a normal.
That it's a normal with actually known mean of mu1 plus mu2 and known variance sigma 1 squared plus sigma 2 squared. So if you look at this, oh hey, this kind of looks right. I've got an x minus mu squared. That's looking good. So what we can do is maybe, let's look at this and let's try to pull out x dependence and then be left with the t integral to do. But you can begin to see this is kind of looking like what we need. I have an x minus mu squared. I'm dividing it by the wrong thing. I've got cross terms. All right, it's going to be a lot of algebra. But let's see if we can get this to work out. Okay, so we've got 1 over 2 pi sigma 1 sigma 2 integral minus infinity to infinity e to the minus u squared over 2 sigma 1 squared e to the minus, now I've got to be very careful as to how I write all of this. So I'm going to expand things out, and I'm going to keep the x minus mu together. Because I expect at the end of the day, I'm going to get something that looks like x minus mu. So I have minus x minus mu squared, and I'm going to have my cross terms. Then I'm going to have minus 2u x minus mu plus u squared all over 2 sigma 2 squared du. Okay, I've just expanded things out. Okay? Please be watching the algebra closely because I could easily make a mistake in through here. All right, any mistakes yet, or is this looking good? Okay. So now the question is, how do we continue the algebra? I can pull out, if I want, the negative x minus mu squared over 2 sigma squared. I can pull that out of the integration, right? Because that has no u dependence. And I've got a u squared, a minus 2u x minus mu. Does that look like anything? Well, I've also got the u squared over here. So what I want to do is I want to put things together. All right? So let's pull out the 1 over 2 pi sigma 1 sigma 2 e to the negative x minus mu squared over 2 sigma 2 squared. Minus infinity to infinity. And now we're going to use some new notation. This is getting very hard to visually read because of a fraction in the exponential. This is why we often use the phrase exp. That means the exponential of what comes inside. So let's look at the u squared term. We have a u squared over 2 sigma squared with a minus sign. We have a u squared over 2 sigma 1 squared with a minus sign. So we'll have a minus quantity 1 over 2 sigma 1 squared plus 1 over 2 sigma 2 squared u squared. Right? The next term is going to be minus and a minus. I'm going to keep the minus sign outside. So I'm keeping the minus sign outside. The next time will be minus 2x minus mu over 2 sigma 2 squared u. Okay. So I'm just grouping things together with a big space. Okay? Well, it's not a big space because we don't have enough blackboard area here, but what should we be thinking about putting in that space? Complete the square. This goes back to our days of the quadratic formula. We want to complete the square. We have sort of like something u squared minus something u. We want to make it a square. If we make it a square, it's going to be an easy integral to do. So what do we need to do? Let's just call it plus b, b squared and minus b squared. We'll figure out later exactly what we need to complete the square. Can you tell me what b is going to depend on? It's going to depend on. It's going to depend on x minus mu. What else is it going to depend on? The variance of sigma 1 and sigma 2. So when you have something like this, it's not necessarily a bad idea to have subscripts on b for just notational purposes so you know what it is. Let's call that a squared. Just so what we have now is a squared minus 2x minus mu over 2 sigma squared, which this is a squared u squared, minus this u plus b squared. And we want this to essentially become a u minus b squared. Okay? Oh, thank you, yes. Can you figure out what a and b should be? One of them is easy to figure out. Which is easy to figure out, a or b? A. You know, I tell you, a is just 1 over 2 sigma 1 squared plus 1 over 2 sigma 2 squared. All right, so now we just have to complete the square and see what do we need to get this to be the case. So you can now figure out exactly what b is. I'm not going to do that calculation. I'm going to just continue. And, you know, it's done in full glory and glory in the book. You can go and look there. E to the negative x minus mu squared over 2 sigma 2 squared. Now, we've added the b and we've subtracted the b. Now we have a minus and a minus, so a minus and a minus becomes a plus. So we'll have a e to the b squared, right? And now what are we left with? We're left with now an integral from minus infinity to infinity of e to the negative au minus b squared du. Can we figure out what this integral equals? So can we figure out this integral? Does it look, yes?
It's just it's a normal time without the normalizing factor.
It's a normal without a normalizing factor, and we just have to be careful how we write it. So the way we should write this is the following. E to the negative, I can write b as a times b over b. And so I would have a u minus b over a squared. Right? This is the same as e to the negative u minus b over a squared divided by 1 over a squared. Right? Is this a normal? Am I missing anything? Okay, I'm missing the normalization constant. I'm also missing one other thing. I'm missing the factor of 2, right? How do I get the factor of 2? Well, I can put in a 2 over here and then multiply by 1/2. And so this is equal to e to the negative mu u minus b over a squared divided by 2. Now I have a 1 over 2, a 1 over a squared, so a 1 over square root of 2a squared. Right? So after doing some algebra, I've now written this as a nice normal density minus its normalization constant. Can I evaluate that integral? I'm now integrating a normal without its normalization constant. Yes?
Which it's 2 times 1/2 times 1 over a squared.
Yes.
Okay.
And then the 1/2 times 1 over a squared becomes 1 over root 2a squared. You can see why I do not want to write all of these constants on this limited blackboard. Okay? There are other ways to do this calculation. I like this method because it shows you a lot of good ways of changing variables. And it shows you the idea that there's a lot of integrals where if you can just show that it equals a probability density, you're done. What's the integral of this? Well, I should have a 1 over square root of 2 pi standard deviation squared. I don't have it, so if I put that in, I then have to multiply. So this integral here, let's continue the mess, is just the square root of 2 pi times 1 over square root of 2a squared. And now you just plug in what a is, you plug in what b is, and lo and behold, after the dust settles, you will get that it is a normal with the predicted mean and the predicted variance. Okay. All you have to do now is figure out what is b, what is a, and then just do the algebra. All right, so it's done in full glory in the book. As you're looking at this, what case would have made things a lot easier to study? Yeah, if it was the standard normal, things would have been so much nicer. You know, I wouldn't have any of the mu's. These two numbers would be the same. I wouldn't have to worry about different factors. I'm pretty sure I don't have any physicists here, but any physics people? Okay, do you remember resistors in series and parallel?
Yes.
Or center mass problems? So if you've seen stuff like that, this is the way you're combining these things. And that's really the same kind of calculation. Alright, so we've proved a major result. But I have actually omitted something from today's lecture that I really should have proved. Otherwise, our notation is horrible. There's something about the normal distribution that I have not proved. So I gave you the definition of the density for the normal. And whenever you see a random variable, what are you supposed to say to it?
What's mean and variance?
What is its moments? What's your mean? What's your variance? Right? Did we prove the mean and the variance? No. We're using highly suggestive notation. Sorry, if the mean is not mu, if the variance is not sigma squared, our notation sucks. Right? This would just be horrible notation. It would be on the order of, I think, the worst notation in mathematics. What is 1 over cosine? And what's 1 over sine? That's always bothered me. Right? You should not be putting cosine with secant and sine with cosecant. So maybe we've just made another mathematical blunder. Maybe we just have bad notation. So we should really prove that the mean and the variance are what you expect. So prove mean of normal mu sigma squared is mu, and variance is sigma squared. Alright. There's lots of ways to do this calculation. Essentially, all we have to be able to do is do it for the case of mean 0, variance 1, and we're fine in general. So, let's study centered moments. So, the uncentered moment, mu k, is the